Hello and welcome to InsideWi-Fi, Video 11. The power of antenna gain in Wi-Fi. A common misconception is that Wi-Fi antennas amplify the signal. In reality, Wi-Fi antennas are passive devices. They do not increase the signal's power. Instead, they reshape and direct the existing radio frequency energy, concentrating it in the desired direction to improve coverage, signal strength and communication efficiency. Ultimately, understanding antenna gain empowers engineers to make informed decisions when designing and optimizing Wi-Fi networks, helping them achieve the best possible performance for their specific deployment environment. For Wi-Fi beginners, it provides a solid foundation for understanding how antennas influence wireless coverage, signal strength, and overall network performance, making it easier to grasp more advanced Wi-Fi concepts. Now that we understand why antenna gain matters, let's explore what antenna gain actually is. What is antenna gain? Antenna gain describes an antenna's ability to focus radio frequency energy in a specific direction. It is typically expressed relative to an ideal isotropic radiator, which radiates energy equally in all directions. A higher gain antenna concentrates RF energy into a narrower beam, increasing the signal strength in the desired direction. This is similar to a flashlight, where a reflector focuses light into a narrow beam, making it appear brighter and more intense. The flashlight does not create more light, it simply directs the existing light into a smaller area. Higher antenna gain concentrates RF energy into a stronger, more focused signal, improving long-distance communication and helping reduce interference from unwanted directions. Antenna gain is typically measured in decibels, relative to an isotropic radiator dBi. How antenna gain shapes your Wi-Fi. The antenna gain controls your network's range, signal strength, coverage pattern and beam width. What is a network range? Network range is the area, or maximum distance, within which devices can communicate reliably with a Wi-Fi access point or router. What is signal strength? By concentrating RF energy in a specific direction, higher gain antennas deliver stronger signal strength to distant devices. This can be crucial for overcoming physical obstacles and minimizing interference. What is coverage pattern? A coverage pattern is the area and shape over which an antenna radiates or receives RF energy, indicating how the wireless signal is distributed in different directions. What is beam width? As antenna gain increases, the signal's beam width, the angle over which the antenna emits a significant signal, narrows. This makes precise aiming more important, especially for high gain, directional antennas. Range versus coverage. Higher gain antennas squeeze the wireless signal into a much tighter beam. By focusing the energy, the signal can travel significantly farther in one specific direction, making it perfect for long-range or point-to-point links, like connecting two separate buildings. However, this is always a trade-off. Stretching your signal farther in one direction means pulling it away from others, reducing coverage in other directions. Signal strength versus beam width. Signal strength and beam width are locked in an inverse relationship because the same RF energy is redistributed over a smaller angle. If you change one, you automatically change the other. As beam width narrows, signal strength in that specific direction increases. What are lower gain antennas? Lower gain antennas spread the signal more broadly and evenly in all directions. They're perfect for providing wide coverage within a single room or a general indoor area, though their overall range will be shorter. Omnidirectional versus directional antennas. A tale of two patterns. The gain characteristics are often tied to the type of antenna being used. Omnidirectional antennas. An omnidirectional antenna radiates RF energy nearly equally in all horizontal directions. Unlike an ideal isotropic radiator, which exists only as a theoretical reference, an omnidirectional antenna has a donut-shaped radiation pattern, providing a full 360-degree horizontal coverage. They are best suited for general indoor environments, where devices are spread out around the access point. Think of an antenna that radiates energy evenly in all directions, similar to how a candle emits light. In technical terms, this is called an isotropic radiator because it has no preference or focus in any direction, meaning it has no directivity. An isotropic antenna is considered to have no gain, which can be expressed as x times 1. This means the energy is distributed equally in all directions, with no amplification. In decibel terms, this no gain state is defined as 0 dBi. Directional antennas. A directional antenna, also known as a beam antenna, transmits signals primarily in a specific direction. Unlike omnidirectional antennas, directional antennas offer higher gain, which results in a stronger signal and extended range within the targeted coverage area. These antennas have higher gain, example, 8 dBi, 15 dBi or more. They focus the signal into a concentrated beam, much like a flashlight. They are ideal for extending range, in a specific direction, creating point-to-point connections, or covering long narrow spaces like corridors. They require careful alignment, to ensure the signal is directed exactly where it's needed. Think of placing a mirror next to a candle. The mirror changes how the light is distributed, giving the candle a sense of direction. One side of the room, behind the mirror, becomes dark, while the opposite side appears twice as bright, thanks to both the actual candlelight and its reflection. Antennas work similarly to mirrors. Just as mirrors don't generate light, but simply reflect and concentrate it in certain directions, antennas don't produce radio energy, they redirect and focus it. This property is known as gain. No additional energy is created, it's simply concentrated in a specific direction. For example, if a mirror redirects half of a candle's light to one side, that side appears twice as bright, representing a gain of 2x. The same principle applies to antennas. They intensify signal strength in certain directions by focusing existing energy. Gain versus signal strength. If the goal is to cover an entire room evenly, without focusing the signal in any particular direction, an omnidirectional antenna is ideal. Antenna gain refers to redirecting energy from some areas to strengthen it in others. As the dBi value increases, the antenna focuses RF energy into a narrower beam, providing greater range and stronger signal strength in the intended direction. 2 dBi gain antennas are used for indoor coverage, 5 dBi gain antennas are used for larger rooms or offices, 8 to 12 dBi gain antennas are used for outdoor point-to-point links, 15 plus dBi gain antennas are used for long-distance wireless bridges. Choosing the right antenna and gain. For sending a signal to a distant specific location, a high-gain directional antenna is the best choice. It focuses RF energy in one direction and needs careful alignment to ensure effective communication with the target area. Antenna positioning. Proper antenna placement is crucial for stable signal transmission, particularly over long distances with directional antennas. Antennas should be firmly mounted to avoid movement, and a clear line of sight between them must be maintained. Even minor misalignments with directional antennas can significantly impact performance. Choosing the right gain for your needs. There is no universally best antenna gain. The right choice depends on your coverage requirements and deployment environment. For broad indoor coverage, example for a home or small office, a lower gain omnidirectional antenna is generally the better choice. For long distance links or connecting separate buildings, you will need a high gain directional antenna. Always consider obstacles like walls and floors, which can weaken Wi-Fi signals. While higher gain can help penetrate some barriers, maintaining line of sight is always ideal for optimal performance. Finally, ensure your chosen antenna is compatible with your Wi-Fi device's frequency bands, such as 2.4 GHz, 5 GHz or 6 GHz. Higher gain is equal to narrower beam, which is equal to longer range. Lower gain is equal to wider beam, which is equal to shorter range. Let me know your thoughts in the comments if you found this video informative and helpful. In the next video, let's discuss about 802.11, the forgotten foundation of wireless connectivity. Thank you for watching.